neutron stars or pulsars. We can observe these stars, but we can't see them. We can't see them directly, but we are sure of their existence. To tell you about these stars, how do they form? How do they live? And what are the extraordinary properties that distinguish these stars from other stars? I'll talk about all of them in detail, so let's get started. To explain neutron stars, I would like to start by saying that stars are theoretically or philosophically living beings. They are born, they grow, they need to consume energy to live. That is, they need to feed. They feed. And when they can't find energy and matter to feed on, they die. Our sun will die one day, and all the stars you see in the universe will die one day. But the way stars die is directly proportional to their mass. The way stars die differs according to their mass. For example, small stars like our sun turn red when they are close to dying. Stars use hydrogen as a source of energy. They convert hydrogen into helium. They convert thousands of tons of hydrogen into helium every second all the time. For example, our sun is like a huge fission reactor. But one day, this huge fusion reactor is going to slowly run out of hydrogen. And as a result of that, it's going to accumulate significant amounts of iron in its core. And stars can fuse all the elements from hydrogen to iron. But there's a very serious problem with iron. There is no serious benefit to you from fusion of iron. So when you start to accumulate significant amounts of iron in the star, the fusion reactor will no longer work properly. At which point, the gravity at the center of the star will prevail and the star will collapse in on itself. But in small stars like our sun, this process is not very bloody. When the day comes, it will turn into a red giant. As soon as it turns into a red giant that swallows the Earth, it will slowly collapse into itself and turn into a small pale calm star that we call a white dwarf. But for a star that is much more massive than our sun, for example, a star that is 25, 30, 40, or even 50 times more massive than our sun, this death process will be very conflicted and very destructive. Because when a supermassive star dies, it collapses so fast that it dies in a massive explosion that we call a supernova. An explosion so massive that it creates such a serious destruction that it can blow a hole in the middle of the galaxy. Fortunately, we have not had such an explosion very close to our world, but we have seen an explosion that could blow a hole in the very edge of our galaxy. Even if it's a supernova, we can observe it from Earth in time. After such massive supernova explosions, all that is left of that star are the black holes that you all know so well. But not all stars end up like this. There are some stars that are too massive to become white dwarfs, but too small to become a black hole. And if you ask, what happens to these in-between stars? What happens to them? Is the neutron star that follows a type 2 supernova. For a star to become a pulsar, a neutron star, its mass should be at least 10 times that of our sun. And a star traveling at these levels will run out of hydrogen. Then it will come to iron. And when iron is no longer capable of fission, the horrible end begins to emerge. All the iron begins to collapse in on itself due to its own gravity. This happens at such a high speed that suddenly the star's core is outside the outer. This gap causes the outer layers of the star to hit the core at an extremely high speed. This impact causes a massive explosion, which we call a type 2 supernova. The star ejects most of the material from its outer surface into space, leaving a core of pure neutrons. So it's like our sun. A star 15-20 times more massive will explode into a tiny neutron sphere 15-20 kilometers in diameter. A neutron star is made up of pure neutrons, at least 95% or 98% neutrons. So where do all these neutrons come from? It comes from the gravity at the center of the star is so intense and so high that the electrons circulating around the atoms cannot escape this gravity, and the electrons in the atoms start to fall. There are protons and neutrons in the nucleus positively charged. What happens when you collide a proton with a negatively charged electron is that they are neutralized and you are left with pure neutrons. Neutron stars are very small, but they are also very dense. They are incredibly small. Naturally, they can be about 15-20 kilometers in diameter, but they can also be up to 50 kilometers in diameter. To give an example, for example, if you turn our sun into a neutron star, it will be 600-700 meters in diameter at most. It will be so small, you can hide it in a gigantic stadium, but you can't deal with it because there's still a mass of a gigantic star there. Neutron stars are incredibly dense, tens of thousands or even hundreds of thousands of tons per cubic centimeter. To give another example, if you take a piece of a neutron star the size of a sugar cube, you can't carry that piece because that piece weighs several million tons, many times heavier than anything. You know, neutron stars are very small, but the gravitational pull is still there. The gravitational pull of the star is still clearly there. That's why it's extremely dangerous to approach a neutron star. You know that despite the high gravity of black holes, there is a lot of radiation around them. It's the same with neutron stars. Neutron stars are attracted to the remnants of the old star left over from the explosion. They have such an intense gravitational pull that the gas and magnet around neutron stars start to compress, and the neutron star's terrible gravitational pull ionizes and converts these jets into gamma radiation, making the star look like a ticking clock from a distance. Neutron stars are also the most accurate clocks in the universe. They spin around at a terrifying speed, some of them spinning at 50 revolutions per second. Neutron stars spin around with tremendous stability. Once upon a time, there was a massive star out there, and the star was spinning around. So a star that was once a quadrillion kilometers in diameter dies, and only 15 kilometers in diameter remains. If the nucleus remains, the rotation continues, but the rotation also becomes terribly fast, of course, as you can imagine. It is because of this incredibly fast and stable rotation that neutron stars are really perfect clocks that you can use hourly. Neutron stars spin at a very stable speed and emit very high amounts of gamma radiation from their poles. And that's one of the most important reasons why we can see them. We can't see neutron stars with optical telescopes because they are extremely small. They are not black like black holes. They can radiate light around them, but because they are so small, it is almost impossible to see them, but we can hear them very clearly. That is the sound of these stars recorded from radio frequencies. Neutron stars rotate around very fast and emit radiation. With the latest techniques, they can be located, and even their density and mass can be calculated.